Hello everyone and welcome to the next and probably the last lecture in the series of lecture on data path design. In this series of lecture, we are discussing about different data path circuits such as adder, multiplier and the balance shifter. We have already discussed about the adder, basic idea of binary addition, half adder, full adder, various ways of implementing full adder at the logic level and the circuit level. Then we saw multiple addition. We saw two circuits for multiple addition, ripple carry adder, and carry loop adder. Then we know that there is a limitation on ripple carry adder and carry loop adder. That's why when it comes to the wide adders, we go for some different configuration. We saw three type of such adders: carry skip adder, carry select adder, and carry save adder. And then in the next lecture, we saw the multiplication, basic idea of binary multiplication, and we saw how iterative addition ultimately leads to the multiplication. Then the circuits to implement that algorithm. Then we saw array multiplication. Today we are going to talk about binary shifting. So the agenda will be, first we talk about the arithmetic operation itself and what is the significance of this operation, what exactly binary shifting means. Then we will see circuits to implement the binary shifting. So here the first question is what is bitwise shifting? And so you might have come across this term when you might have studied your processors and controllers. So this is one of the important operation when it comes to the processor or controller. We'll see what is significance of this operation later. But let's consider what exactly this operation is. Suppose I have one number. Let's assume the number is 1101. Then I have two options. Either I can shift this data on in the right word. When I shift this data rightward, then this bit will come here. This bit will take this position, and this bit will take this position. Then number will become 0, 1, 1, and then we'll append 0 here to the fourth location or to the MSB, right? So that is shifting in one direction. That's a right shift. Now I can shift bit in the left direction as well. So in this case, this bit will take this position, this bit will take this position, and this bit will take this position. So the number would be 1, 0, 1, and this will be replaced with 0. So this is left shift operation. Now if you have grabbed the basic idea of shifting, let's look at the shifting in much details. You might have studied the shift operation in your digital electronic course in the lower semester, but let's look at it into details. There are two types of shift operation. One is called as logical shifting, and second one is called as arithmetic shift. The basic difference between these two is in the logical shift, you retain leftmost or rightmost bit. So you do not retain leftmost or rightmost bit. You just shift and you go on appending zeros after shift. If you shift on left, then you go on appending 0 rightward. If you shift on right, then you go on appending 0 leftward. In arithmetic shift, when you shift a bit, you just copy the leftmost bit or the rightmost bit instead of appending 0. You will see this with example, but let's at this point of time you should know there are two types of shift operation: logic and arithmetic. So again, in logical there are two types of operation. One is left shift, second is right shift. In arithmetic as well, there are two types of shift operation: left and right. So if you look at this as a whole, there are four types of shift operation: logical left shift, logical right shift, arithmetic left shift, and arithmetic right shift. So let's see all these four operation. We apply all these four operation on the number that we are considering here, which is 1101. Now let's start with shift left logical or shift left logical. In this case, I am going to shift it by 2 position. Okay, so for that, 110, let's shift it by 1 position first. Okay, so left shift can also be written like this with double arrows. So if I shift it once, so I'm going to shift this one, so this will come here, this will come here, and this will come here. Now here the number will become 101, as this one comes at this position, this 0 comes at the next position, and 1 comes here. Okay, so if this is A3 and this is A0, this A2 is shifted to A3, A1 is shifted to A2, and A0 is shifted to A1. Now this A0 is vacant and it is filled with 0. So this is one shift. So again, if I shift this one more time, so if I shift it by 2, so what actually I am doing? I am shifting this one more time. So this 0 will come first, and then the 1, and then this 0, and then the last 0. Sorry. So this is the left shift by 2. So in this case, one thing I want you to know is when I shift here, my rightmost bit was 1, but after 2 operation, it has become 0. Or after shifting it twice, it has become 0. So we have not retained it. This is something I want you to remember. Okay, so this is left shift by 2. And this is logical left shift, SLL. So shift left logical 2 times. Now 1101 is a second. Now let's apply shift right logical twice, SRL2. Now in this case, if I do SRL1, then its answer would be, so I have to shift on the right logically. So this would go here, this will go here, this will go here. So the number would be 0, 1, 1. And then this vacant will be filled with 0. Now if I do SRL1, SRL2, that means I have to do SRL1 on this, or it is equivalent to SRL2 on this, right? So it would become 0, 0, 1, 1. Now again, one more thing I want you to remember. See, if I consider this to be a negative sign number, then this was negative. After shift operation, 0 has appeared here, so it has become positive. So it is not retaining its leftmost bit. Okay, so in logical operation, it is not retaining its leftmost or rightmost bit. Now let's look at the arithmetic operation. So same number we consider 1101. Now the third type is shift left arithmetic twice. Now first I'll perform shift left arithmetic once. So this answer would be, so I'm shifting on left, right? So here this will come here, this will come here, and this will come here. So my number would be 1, 0, 1. Now this term has, this place has become vacant, but I won't append 0. But what I'll do is I'll keep this one as it is, right? So the same one is copied here, and also it is retained there. Now if I perform SLA2 or SLA1 on this number, or SLA2 on this number, it's equivalent. So it will become 0, 1, 1, 1. So this 0 has come here, this 1 has come here, this 1 has come here, but at the same time this 1 is copied here. Okay, so if I perform SLA2 on this directly, it will be 1, 1, and then 1, 0, right? So 2 times I have to copy this here, here, and the 0 is shifted, right? So here one thing you have to remember, you have to observe here is 1 is retained. This position, the rightmost bit is retained if there's a left shift. Now let's see final operation on 1101, which is shift right arithmetic twice. So if I perform SRA1, that is shift right once. So if I'm shifting right, so it is going in this direction. So the number would be, this 1 will be gone. So it will become 0, 1, 1. Now this is blank. So this vacant place is again copied with this. So it will be 110, 1110. Now if I perform SRA2, then the same thing will happen again. 1 1 1 1. So you can see here 1 is retained, which was earlier there. So we can say in arithmetic right operation, your leftmost bit is retained, and arithmetic left shift, your rightmost bit is retained. Okay. Now, what is significance? What is use of this binary shifting? So, binary shifting in the left direction is equivalent of multiplication, and binary shifting in the right direction is equivalent of binary division. Let's consider this with an example. Suppose I want to perform 3 into 4, that is 12, right? So, if I consider this number 1 1, if I consider this binary multiplication to be 1 1, and then if I consider this to be binary 100. Now, the answer would be it's 1100. Now, if you look at this answer, I can instead of performing the multiplication or multiplying by bit and then the shift operation that we have seen in the previous lecture, I don't have to do that. The best option to do this operation is I'll replace this 4 or 100 as 2 to the power 2, right? Because 2 is the base of binary to the power 2. So if I want to multiply, what I have to do, 1 1 is the multiplicand and 1 0 is the multiplier, which is nothing but 2 to the power 2. So I have to shift it left by the power of this multiplier, right? So power of 2, which is equivalent to the multiplier. So here the power of 2 is 2, which is equivalent to the multiplier. So I have to shift it left. So the 1 will come here, this 1 will come here. Now again this position will become vacant, so 0 will be appended here. So it's 1100, which is nothing but 12, binary 12, right? So we can conclude that binary multiplication is equivalent of left shift operation. Now let's assume one more example for division. So the right shift operation is equivalent of binary division. So let's consider an example. Uh, let's assume 16 divided by 8 is 2. Let's see how it is implemented in binary. So 16 can be written like 10000 divided by 8, which is 1000. Now here 8 can be written as 2 to the power 3. Now, as per the rule or as per the logic we discussed, we have to shift this multiplicand, sorry, the dividend by the power of 2, which is equivalent to the divisor. So 2 to the power 3 is equivalent of 1000. So I have to shift this on the right by 3 digits. So this would go, and this would go, right? So this 0 will come here and 1 will come here. So it is 0 and 1. Obviously, it will be 0 will be appended. So it's equivalent, or it's effectively 1 0, which is nothing but 2, which is equal to the which is equal to the which is according to our calculation 2. So we can conclude here that when you shift leftward, you are actually multiplying by the power of 2. When you shift rightward, you are actually dividing by the power of 2. So this is a logical shift that we have discussed. When you consider the arithmetic shift, the signed multiplication or signed division can be performed using the arithmetic shift. You can take few numbers and you can work on them to for the binary for the arithmetic shift, and you can verify the answer. Now the next question is how I would implement this circuit. So when I think about it, the first circuit that can come to my mind is the shift register that I have studied in digital electronics. So if I consider serial in, serial out, then by using the simple circuit, for every cycle, my data bit can be shifted leftward or rightward, and I can implement the left shift or the right shift operation. But there is one problem with such kind of implementation. The problem is, suppose it's a 64-bit data and you want to shift by 32-bit, or you want to shift by 50-bit, then probably you have to wait for 50 clock cycles to occur to shift your data to the left or to the right. So it's a lot of time when you consider the processor or a controller. So if you are doing it sequentially, I can conclude that if you are doing it sequentially, then it takes a lot of time to implement this logic. So we have to look for a circuit which can do it using a combinational circuit. So such circuit is a barrel shifter. Okay, so we'll go on developing the barrel shifter circuit, but before that, let's start with the basic idea of shifting and how we are going to implement using combinational circuit. So if I uh, if I implement using a combinational circuit, the first circuit that might come to my mind. So let's do it for the fixed shift operation, which is not practically implemented like that. We don't practically implement like this, but this is a very rudimentary idea. This is a very raw idea of implementing a shift operation. So suppose I consider this circuit. If I want to shift by 2, then you can see here this is the input part and this is the output part. So you are to shift right by 2. So this A2, A3, we will actually lose these bits, and then this A1 will come here, and this bit will come here, and this B0, B1 will become permanently 0. So if we consider our earlier example 1, 1, 0, 1, then this 0, 1 won't be considered, but this 1 will come here, 1 will come here, and this will be 0, 0. So it's 0, 0, 1, 1, right? So this is as per the result that we have observed earlier. So similarly here, if you want to shift logical on the left side by 3, then A3 will come to B0 and the rest of the bits will become 0. Okay. When you want to implement arithmetic logic, arithmetic shift, this exactly same base there. Here I am doing shift by 2, shift by 2. This circuit is implemented same. The only difference that instead of these zeros which are added here, we copy the same bit, that is A0 is copied at all the previous locations. So we put A0 at the vacant places, right? We put A0 at the vacant places instead of putting zeros. Same is the case with the shift left arithmetically by 3. So the circuits are exactly similar, but instead of putting zeros in the vacant places, we put A3. You can see the A3 has been put here, right? So this has been the idea. This is the simplest, very raw implementation. So we will have for left shift, you will have one circuit. For right shift, you will have another circuit. For left shift by 1, you will have one circuit. For left shift by 2, you will have another. It's like this, you will have a different circuit for every shift operation. So if I want to implement it for the 32-bit processor, how my implementation would look like? Okay, the implementation would look like this. Suppose this is a 32-bit processor which has a 32-bit input. So then I have this array of SRL operation. Now this is just for shift right logical. Just imagine we have shift right arithmetic, we have shift left logical, we have shift left arithmetic. So will have such 4 circuits. This is just for one operation, SRL1. Now in this case, what we'll do is we'll implement first a circuit for shift by 0, circuit for shift right by 1, shift right 2, shift right 3, shift right 4, shift right 5, up to shift right 31, shift right logical 31. So when I apply input here, the input is applied to the all circuits simultaneously, and they will give output as per their operation. I mean, the SRL2 will actually shift this input by 2, this will shift by 1, this will shift by 0, that is there won't be shift operation, then the next will shift by 3, then the 4, then 5, then 6, then this final circuit will shift it by 31, and all the outputs are 32-bit outputs. So we'll have all the outputs available at the inputs of mux. Now uh, there will be one shift operation. Suppose I want to shift this data by 5, then it will select SRL5 output out of this 32 inputs. It will select SRL5 output, which is input, fifth input of this mux, and it will appear here, right? So so this is how the circuit, the shift output is selected. Now you are generating all the outputs, and out of which only one is selected to the output, right? So uh, the very first impression that of the circuit on my mind is it's very area consuming. It's a very large circuit to implement. It takes a lot of silicon. It consumes lot of silicon, and that to just implement SRL operation. then we have to implement such 4 circuits. So the area requirement is huge. So it's not area efficient circuit, but obviously it's very simple circuit and uh, it's a very straightforward circuit to implement. But this is not the way we practically implement it. So if I want to implement it practically, I will go for another or a barrel shifter. The design principle comes from here, from this discussion. Instead of having all the shift operation, I will have selective shift operation, and I'll combine this shift operation to get any shift value. So in this case, I'll consider 8-bit data and I'll perform operation from shift 0 to shift 7. Okay. So for this, I'm implementing the same circuit, right? So SRL1, SRL2, SRL4. So for a shift from 0 to 7, for all the shift, instead of implementing 8 shift circuits, I'm using just 3 shift circuits. Okay, this is shifting by 1, this is shifting by 2, this is shifting by 4. And I will have 3 mux. I'll explain the circuit with one example. Suppose I want to shift of 5 like we had in the previous case. In the previous case, when we wanted to have shift of 5, we had all the outputs available, out of which we just selected one. In this case, we won't have all the outputs available, but instead of that, we'll give appropriate select input so that only those SRL circuits which are supposed to work will give the output, and those output will be selected. Let's discuss this with an example. Suppose for this we want to shift by 5. So where circuit S2 is 1, that's MSB, 0, 1. This is LSB, right? So first this A7 to A0 is applied here. Then when it goes through, it passes through SRL1, it generates the output which is A7, A0 with 1-bit shift. And here it is directly applied here. But now this A0 is 1, so it is going to select this input. So at the output, I will have A7 to A0 shifted by 1 position, right? Shift right by 1 position. Now when this input is applied here, this SRL2 will generate A7 to A0 and then SRL2 the shift right. So it has already been shifted by 1 location and 2 more shifts will be applied. So it will be shift by 3 position. And for this input, it is directly applied. So for this input, it is A7 by A0, A7 to A0 with 1 shift. But because this is 0, it won't select this, but it will select this. So it will pass this here. So at this point, we will have again same. So here it came through this. So if I look at this, so it will give you better visualization of this. Okay, so here the input came through this. It came here, then it passed through this. Okay, and till now it is A7 to A0 shifted by 1 position. Now when it comes here, it is shifted by 4 position more. So it was shifted by, so when it came here, it came here, it was shifted by 1 position. Now because it's SRL4, so it is effectively shifted by 5 position. And at this position, it is shifted by because this at this input is shifted by 1 position only. Now because this is 1, so this output will be selected. So effectively it is shifted by A7 to A0 will be shifted by 5. So this is how a 5 shift is achieved, right? So the basic idea is if you are doing it for 8-bit, then you implement all the shift which are equivalent to the power of 2. So because this is a 8 shift operation and I'm for 8 means I'm going to work on the 3-bit. 2 raised to 3 is 8. So first I'll implement 2 to the power 0, that is 1, then 2 to the power 1, then 2, then 2 to the power 2, 4. So that's why SRL1, SRL2, SRL4. Suppose if I were to perform on 4-bit, then probably the next SRL would be 8, 2 to the power 3. So with the combination of this 1, 2, 4, 8, I can have any shift value from 0 to 15. So that's the idea of barrel shifter. I hope it is clear to you. You just go through it and verify this with various combination. So I'll give you one task here. You just try to implement circuit for 32-bit operation and try to figure it out how the 27 shift operation will be carried out using different combinations of mux and the select lines. Okay, now here we come to the final point of the discussion where we are going to see circuit level implementation of barrel shifter. Now, when the barrel shifter are implemented using circuit, they are implemented either in M cross N form, where N is output, M is input, and normally this M value is either twice of N or it is N. So normally you will find it 2n cross n or n cross n. So first we will see 2n cross n circuit and then we will go for n cross n circuit. So here you can see there are 8 inputs A0 to A7 and there is 4-bit output B0 to B3. Now here for 0 shift A0 will be directly applied to B0, A1 will be applied to B1, A2 will be applied to B2 and A3 will be applied to B3. And so on. So let's see one more example for this shift by 3 operation. You can see here A3 will be applied to B0, A4 will be applied to B1, A5 will be applied to B2, and A6 will be applied to B3. Right? So that's a simple operation. This is a simple truth table to understand. Now let's look at the implementation of this. Okay, implementation of this looks like this. Now apparently it is very complex circuit, but it's not that complex as it looks. Now let's try to implement the circuit. Let's see how to draw it. Okay, so we'll first start with the shift operation. So for shift operation, you just try to look at the input and output combination. Always remember one thing: when you want to draw circuit for barrel shifted, you just check for input and output combination. For shift 0, A0 input, B0 output, A1 input, B1 output, A2 input, B2 output, A3 input, B3 output. Okay, so here while implementing this, we'll have one shift line. Okay, so here first you have NMOS with A0 input and B0 output, A1 input, B1 output, A2 input, B3 output. So let's not think about the output here. You just shift and then you just draw the NMOSes and the input will be A0, A1, A2, A3. For shift 1, you draw the NMOSes, 4 NMOSes, and the input will be A1, A2, A3, A4. Then for shift 2, it's so you just for shift 2 you just see A2, A3, A4, A5. So you have to draw for A2. So A2 is already drawn here. So there will be A2, then A3, A4, and A5, and so on. Now what you have to do is for B0 you have to connect all these A0, A1, A2, A3. So for B0 you have to connect all these A0, A1, A2, A3, A4. So you have to connect this A0, this A1, this A2, this A3, and this A4 to the B0. That will give you B0. Okay. So try to draw the circuit, then you will understand this, right? So the operation is very easy. So let's look at one shift operation and then we'll go ahead. So let's assume that we want to perform shift 2 operation. So we are expecting output to be A2, A3, A4, A5 according to the truth table. So if I want to have the shift operation by 2, so I'll make this 1 and the rest of the shift operations will be 0. So this is 1, so this is on, this is on, this is on, this is on. So these all the NMOSes they will present a short resistance path for the input to the output. So they are the NMOSes acting as a switch. So this input A2 will go to the output, which is ultimately connected to the B0. This A3 will go to the output, which is connected to B1. A4 is connected to the output, which is connected to B2. A3 is connected to the output, which is connected to B3. So that's a simple implementation. So if you look at the working of it, then it will be easier for you to implement it. Okay, try to understand the operation and then to try to implement. So first try to figure out the working of this for different shift operation, and then you draw the circuit. It will be easier for you to draw the circuit, right? So I guess that's a very straightforward circuit. Not much to explain about this circuit. It's a simple NMOS connected in a cascade, and there is basically this type of structure. So all the NMOSes which are operated or turned on by one shift signal are connected together. Their gates are connected together here, gates of all NMOSes which are active during one shift operation are connected together. Their inputs are is connected to A0, A1, A2, A3, and based on which shift operation you are performing, the outputs are connected accordingly. So you just draw the circuit. It will be the circuits are very easy to draw once you understand the operation. Okay, so this was a logical shift operation. So we'll move ahead and we'll see the implementation of uh, arithmetic shift operation. And because we have already seen 8 cross 4, so here we will see 4 cross 4 operation. Okay, so here uh, there is a particular way of drawing this circuit. Let's look at how to draw it. Before we look at the circuit, let's first see how to draw the circuit. Now, I am implementing 4 cross 4 board barrel shifters, which has 4 input and 4 output, and which is an arithmetic shift operation. So I have this truth table with me. So based on this truth table and the fact that I know that it's a 4 cross 4 4 cross 4 barrel shifter, I draw the circuit first. So what I'll do is I'll I'll draw first 4 uh, columns and 4 rows. So I have these 4 rows and 4 columns. In every row and column or every position of this array or matrix, I will draw an NMOS. Okay, so you can go on drawing like this 1, 2, 3, 4. So 16 such NMOSes will be there. So you can see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now I'll tell you how to connect these. The connection looks to be a bit complex, but it's not that complex once you follow this technique. Okay, so to make it easy, instead of drawing the NMOS, I will draw just dot to indicate presence of one NMOS. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. These are 16 NMOSes that I have drawn. Now I will start from diagonal elements. So in diagonal elements, so first I will go with shift 0. Okay, so this is, remember, so first diagonal is shift 0. For shift 0, like I told you, when you draw barrel shifter operation, you have to focus on input and outputs. Now I have already drawn the NMOSes. For the first shift 0, A0 input and B0 output. So I have already have NMOS drawn here. I have to just mark A0 at the input and B0 at the output. That's it. Okay. Remember that I have already drawn NMOS. I have to just mark A0 and B0. That's it. Right. Then next is A1 B1. So I'll go in the upward direction. I have already drawn an NMOS. I'll write A1 input, B1 output, because these are outputs, right? This is output, so I'll just write this output. Now this is the next in the upward direction according along the diagonal. So here this is input is A2 and output is B2. So this is this transistor I'm talking about. So I am done with these 1, 2, 3. Then the fourth one is this, where A3 is input and B3 output. So here you have A3 input and B3 output. So I am done with the shift 0 operation. The next I have to do is I have to go for shift 1. So I can either go in the upward direction or the downward direction. That's up to me. But I'll go in the downward direction. So I'll go downward and I'll select this diagonal. So for this diagonal, this is shift 1 operation. Now again, we'll start from the first. A1 input, B0 output. So here I come across the first transistor in this diagonal. So this is the first transistor along this diagonal. So here it's A1 B0, right? Then it's A2 B1. So if I go here, then I'm actually looking for this transistor, which is nothing but this transistor. So here you can see A2 B1. Then here it's A3 B2. So it will be A3 B2, right? And then if there are 3 transistors, but I am still left with this A3 B3. So what to do with this? So what I will do is I'll go in the upward direction only. I have to go in the upward direction. So I will go to the first line from this. So because I will skip these and I'll come here. Okay. So here I'll come and there again I'll implement this A3 input, B3 output. So here it is A3 input and B3 output. So this is the transistor fourth one. Now I'll come for the shift or 2. I'll come to the next diagonal in this the same direction, as it is shift 2. So I have to draw two transistors over here. First with A2 input, B0 output, A3 input, B1 output. So here you can see it's A2 input, B0 output, and A3 input, B1 output. Then I have to go in the upward direction, but there are no transistors. So I'll come to the next line, which is this. So here I have to implement A3 B2. So this is A3 B2, A3 input, B2 output, and the next one is this, which is A3 B3, which is this one with the A3 input, B3 output. So then for shift 3, I'll come here. So this is A3 B0. So here you can see it's A3 B0, A3 B0. Then I have to go in the upward direction, but there are no transistor left. So I will come in this direction again. So here I'll come. So it's A3 B1. So it's A3 B1 here, and then it's A3 B2. So this must be A3 B2. So here you can see it's A3 B2, and then this is A3 B3. So the final one, this is final one, A3 B3. So this is how you can uh, draw the transistor, and along this line you can connect their gates, right? So this is how the operation or the diagram will be drawn. So once you draw the diagram, operation of this is exactly similar to the previous one. The only thing is that here, instead of having a straight shift line, we have diagonal shift line. Let's look at one of the operation. Let's look at shift 2. When it's shift 2 is 1, so this signal become 1. So all the transistors whose gate is connected to shift line will be turned on. So this is one, and this is another transistor. And here if I see, this is another transistor which are connected to shift 2. So these are also on. So this is on, this is on, this is on, this is on. Okay. So if this is on, this A2 input, so this there it will provide a small resistance path. So it is as good as a shorted. So A2 is connected to B0. So you will get A2 B0. Yes, truth table first entry is verified. Then this transistor is on, so A3 will be given to B1. So yes, A3 will be given to B1. Second entry is also verified. Then next is A3 B2. So yes, A3 is B2. This is on. So A3, it's due to the small resistance, A3 will be shorted with B2, B3. So A3 B3. So this is how you can verify for different shift operation, right? So its working is very easy for this as well as previous circuit. You should understand how to draw the circuit. That's the important point here. Okay, so this is how I'll suggest you to verify the operation for other shift values like shift 3, shift 0. You can draw, or you can go for 8x8 barrel shifter and try to verify the circuit. Okay, so uh, that's the end of barrel shifter here. I hope you have understood uh, the way the barrel shifters are implemented, and that's the last lecture of this series. I hope you have understood all the circuits that we have discussed. I suggest you to go through the circuits. You try to draw on your own and try to understand their working. If you have any doubt, you just post your doubts in on your WhatsApp group or the Google Classroom. Uh, and thank you for attending this series of lectures. Thank you.